Okay, we are going to work out this question. So it states that in an electrical method to determine specific latitude of vaporization of a liquid, the liquid was heated in an electrical heat, and the state quantities measured under two different operating conditions are given in the following table. So these are the two experiments, experiment 1 and experiment 2. The data we are given is the current flowing in the heater, which is in amps, the potential difference across the heater, which is in volts, the mass of the liquid contains, which is in grams, time of heating, which is for both experiment 300 seconds. First question is as follows: calculate the specific latent heat of vaporization of the liquid. Now, what you know when using a calorimeter to determine the specific latent heat of vaporization of a liquid, we consider the principle of conservation of energy. Now, the principle of conservation of energy is that in this case we state that the energy that is applied by the electrical heater is equal to the energy gained by the liquid plus energy lost to the surroundings. So what I have is solution. So the electrical energy supplied by the heater is equal to let's say the thermal energy gained by the liquid plus heat lost to the surroundings, right? So now, for making the statement easier, I'm going to represent the heat lost to the surroundings as H. So H represents the heat lost to the surroundings during both experiments, right? So let's analyze a bit on our table. Our table contains current which flowed in the heater, the voltage, and the time. So now, what do you think when you see current, voltage, and time in relation to energy? So from the definition of electrical power, right? Electrical power P is equal to electrical energy over time. Now let me make electrical energy subject to the formula. It's simple. Electrical energy is equal to electrical power multiplied by time. Now I just want to use symbols to represent this. So let's see our electrical energy is represented by, let me just say, an arbitrary letter E subscript E is equal to electrical power. We know that power is equal to voltage multiplied by current, so that just gives me VI. So electrical power is voltage multiplied by current, so that is what I represented by V and I multiplied by T, right? So we have electrical energy E subscript E, which is VI T, right? So I'm going to substitute this in this equation, right? So I have VIT is equal to thermal energy gained by the liquid. The energy gained by the liquid is given by M multiplied by the mass of the liquid multiplied by the latent heat of vaporization of the liquid, right? Plus the heat lost to the surroundings. Earlier I alluded to the fact that I will show the heat loss to the surroundings by an H. So plus H, right? So this is our equation. Now what I want is to make VI subject to the formula. So I'll divide both sides by T. to make our calculations easier. Mass of the latent evaporation over time plus reduce the surroundings over time, right? So let this be the first equation to represent the first experiment. Now for the second experiment is simple. We still have now instead of V we have V dash to represent the second voltage, right? And instead of I we have I dash. Instead of M obviously we have M dash. The latent heat of vaporization of the liquid is the same, and the time as you saw was also the same, so it remained as T plus the heat lost to the surroundings. I'm going to assume that it was the same, so H over the time was the same, so I have two equations. Now what you want to do is to determine the specific latent heat of vaporization of the liquid. So what you can do is solve these two equations. So subtract equation 2 from 1. What that leaves us with is, the rate of it close to the surroundings cancel each other out. So what you have is Vi minus V dash I dash is equal to LV over T M minus M dash. We're at this point, right? So we are going to make the latent heat of vaporization as the substitute formula. So that simply gives us with I dash multiplied by time or over the mass of the first experiment minus the mass of the second experiment. So now what you're going to do is simply plug in the values that you had. For the first experiment, voltage multiplied by current, that is 1 multiplied by 12. 1 multiplied by 12. Let me use square brackets here for clarity. For the second experiment, it was 0.8 multiplied by 8. So it's 0.8 multiplied by 8. And this all was multiplied by time, which is 300 seconds. For the first experiment, the mass was 14 grams. Now, as you can see that we want to make 14 grams into kilograms. What we are supposed to do is divide the mass in grams by 1000. So we have 14 over 1000 minus, for the second experiment, it's 9 over 1000. It's just substitution. So let me punch this on with the calculator. Let me turn it on. So we have 1 multiplied by, make two brackets, 1 multiplied by 12 minus 0.8 multiplied by 8. This multiplied by 300 over 14 minus 9. Sorry, this is 1000. My calculator is failing me. Let's try this again. So we have 1 multiplied by 12 minus 0.8 multiplied by 8. This being multiplied by 300. 14 over 1000 minus 9 over 1000. So this gives me 336,000 joules per kg. So this is our specific latitude of vaporization. If you want, you can say it's 136 kilojoules per kg. It's still the same, right? That is for our first for part A. Now for part B, explain why the experiment was repeated for different values of voltage and current. So the reason we repeat the experiment for different voltages and current is to eliminate the heat loss to the surroundings, so as to add accuracy to our experiment. So as you saw during our calculations, they actually cancelled each other out, so that we can accurately determine the specific latitude of vaporization of the liquid. Now for part C, give an assumption made in A. So we assumed that the heat loss to the surroundings for both experiment 1 and 2 were the same, and we did not change H. Right. D, estimate the rate of loss of heat from the calorimeter. Now what they want is theoretically is H over T, right? The rate of loss of heat from the calorimeter. So we can go either to the first equation or the second equation and make H over T substitute formula. So I'm just going to use the first equation. So the first equation, this is part D. First equation is want to make H over T substitute formula. This is simple. Subtract now. This is for the first experiment, right? The value of the voltage for the first experiment was 12. The value of current was 1 ampere. Subtract the mass. The mass for the first experiment was 14. Now remember to put it into kgs. Multiplied by the latent heat of vaporization, which is 136,000 over what? Over the time, which is 300. So this gives us H over T, which is the rate of heat loss to the surroundings. Now let me punch this. So we have 12 multiplied by 1, subtract 14 over 1000 by 336,000 over 300. That gives me minus 3.68 joules per second is the rate of heat loss. Therefore, the rate of heat loss to the surroundings equals 3.68 joules per second. The negative sign just shows that it is heat being lost, right? So that's it for this video.